All right, good morning. This is Physics CP on November 17th, 2020. I'm doing a debriefing on a homework assignment that had the title Momentum and its Conservation. This was actually a photocopy from a list of supplemental problems from the physics course from our publisher. And in particular, it's problem number 6 that I'm going to be explaining. How do you get the answer for this problem? The original problem read, a single uranium atom has a mass of 3.97 times 10 to the negative 25th power kilograms. It decays into the nucleus of a thorium atom by emitting an alpha particle at a speed of 2.10 times 10 to the 7th power meters per second. The mass of an alpha particle is 6.68 times 10 to the negative 27th power kilograms. And here's the question. What is the recoil speed of the thorium nucleus? So there are about 3 parts to this problem that I want to guide you through on how to do. So the first part is if I have a box, and you're saying, well, there's no box in this problem. That's true, but this is to get you thinking about how to solve a certain problem. So suppose I have a box, and inside this box, I have a ball. And when I put the box with the ball on it on a scale, oh man, it shows that I have a mass of 32 kilograms. I'm just making up some random number. Okay, next, I take the ball out of the box and I put the ball by itself on the same scale. And it says, oh, the ball by itself has a mass of 4 kilograms. The question I'm going to pose to you students, and I'm going to do that randomly. Okay, so my question for you students is, if the mass of the box with the ball in it is 32 kilograms, and after I take the ball out, I determine that the mass of the ball is 4 kilograms, what is the mass of just the empty box? Jonathan. And how did you come up with 28 kilograms? I see. 32 kilograms minus 4 kilograms is 28 kilograms. Okay, you're absolutely correct. And I want all you students to kind of hold on to this thought, because this is a key part of doing problem 6, understanding what they're talking about when they talk about uranium, alpha particles, and thorium atoms. So let me try to illustrate to you. I happen to have a periodic table because I'm teaching chemistry when I get done with you guys today. And I suppose I should zoom in a little bit so you can see where we are in the big universe of things. Here is the element uranium. And by the way, let's do a chemistry review right now. How many protons are there in uranium, Siddharth? Man. Jaden, do you agree with that? Nice. That is correct. There are 92 protons in uranium. The atomic number is always the number of protons. The atomic mass is the sum of the protons plus the number of neutrons. And the reason it's not an integer value on the periodic table is because this is an average based on the naturally occurring abundance of the different isotopes of uranium. Nice. Now, an alpha particle, they talk about it in problem 6, and here's the Greek symbol for alpha, the Greek letter alpha, which became our letter A. An alpha particle is basically the nucleus of a helium atom. It consists of 2 protons and 2 neutrons. That's an alpha particle. It is a radioactive piece of a nucleus of an atom. So what's going on here is I'm telling you that uranium is like the box with the ball inside of it. So all of this is the uranium atom. Sorry, I just drew a capital letter U, meaning the box with the ball in it. The ball itself is the alpha particle that is emitted by radioactive decay from the uranium atom. What's left behind is an empty box. And so, back to the periodic table for a moment. If I start with 92 protons and I remove 2 protons, how many protons will I have, Dylan? Yep. And so, looking on the periodic table, element number 90, sure enough, is thorium, which they're talking about in problem 6. So this thorium is the empty box. Okay, if we go back to my analogy here, the thorium is the empty box. So uranium disintegrates into thorium plus an alpha particle being emitted. This is not a chemical reaction. This is a nuclear decay. Okay, this is a nuclear decay. All of this was expected to be basic understanding on your part as you read problem 6. In problem 6, they gave you the mass of the uranium. They said the mass of the uranium is 3.97 times 10 to the negative 25th kilograms. They also told you in this problem that the mass of the alpha particle is 6.68 times 10 to the negative 27 kilograms. Now think back to this simple example here. If I have the mass of the box with the ball in it, and I have the mass of the ball, then by subtraction, I get the mass of the empty box. That's what we're doing here in this problem. They gave us the mass of the uranium. They gave us the mass of the alpha particle. So how do I get the mass of the thorium atom? Tyler. That is correct. You would get it by subtracting the mass of the alpha particle from the mass of the uranium atom. Raise your hands if you did that on your homework. I see 1, 2, 3 hands. 4. Okay, I see a total of 4 hands, hands down. And out of my class of, yikes, 21 students, only 4 hands went up. So already, this is, well, it is what it is, as our president would say. Okay, so the next problem is correctly using your calculator to come up with this math. I need to point out to you, most students have TI brand graphing calculators, and the rest of you, nearly all the rest of you, have Casio type brand. There is almost no difference between the two, but I'm going to be addressing the TI quite a bit because that's what I happen to have as well. When you deal with numbers that are in scientific notation, there are some things you should keep in mind. For example, oh boy. I'm not sure I can give a meaningful example that fits what I want to do immediately. Okay, let me instead tell you this much. You have a button on your calculator that is labeled caret. And caret, of course, means raised to the power of. Raised to the power of. So if I were to type in 2 caret 3 without a calculator, does anyone know what I would get? 2 raised to the third power. Can anyone tell me without a calculator? Zara, go ahead. That is correct. This means 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So 2 cubed is 8. That's great. Some of you students foolishly use this caret for representing numbers in scientific notation. So here you would type 3.97 times 10 caret, and then what? This is wrong, by the way. I suppose if you hit the minus key, then you type in 25. I'm curious. I'm not sure what it will do. So I'm going to find out right now with you. Typing in, and I know you can't quite see this yet. All right, and I can dim this a little. Oops. Okay, so I'm going to type in 3.97 times 10 caret minus 25. And I see on this calculator, this is a TI 84 Plus Color Edition. It correctly put in the 25 as an exponent, even though I put in a minus sign here instead of the exchange key that I should have used. So, oh, maybe not. It says, I have an error. Well, that's not encouraging. So now I'm going to type in 3.97 times 10 caret, and this time, instead of pressing the minus key, I'm going to press the exchange key. Let's see if this corrects that error. So instead of minus, I'm going to do exchange and see what happens. So exchange 25, enter. I said, oh yeah, okay, sure, I'm with you. I understand all this. Now, this is the wrong way to put in scientific notation into your calculator. I don't know if I can show you immediately why that is wrong. I guess the thing to do is just see what happens. I'm going to type in the mass of uranium, 3.97 times 10 carat, exchange key, 25, and please, this is the wrong way of doing it, minus 6.68 times 10 carat, exchange key, 27, enter. I don't know what it's going to say. I know what the right answer is. I don't know if this thing would actually work. So here we go, 3.97 times 10 carat exchange 25 minus, okay, so with a TI 84 plus color edition, it doesn't automatically get you out of the superscript thing. So I'm going to delete this exchange key. And now I have to use like the right arrow key to get me out of exponent. There, okay. Now I'm going to go minus 6.68 times 10 carat exchange 27, arrow to the right, enter. Well, okay. So in this situation, order of operations mean multiplication and division is done before addition or subtraction. In this case, it correctly subtracted the mass of an alpha particle from the mass of a uranium atom. Okay, so in this case, even if you did it the wrong way, you will get lucky, I say, and end up with the correct answer. Might as well write down the answer, right? So thorium mass is 3.90 times 10 to the negative 25th power kilograms. So why don't I show you the correct way to do this instead of always, getting lucky with the wrong way. So the problem is like this. When you use the carat after a 10, your calculator interprets this as two different numbers. Here's 3.97, and really it thinks that this is times 1 times 10 to the negative 25th power. And you're saying, well, there's nothing wrong with that, but there is. And it didn't show up when I did subtraction, but it sure would show up if I were to try, let's say, division. Yes. Let's try division, and maybe you'll see what I mean. Okay. In fact, we'll even use these very same numbers. If I type in 3.97 times 10 carat exchange 25, and instead of subtracting, I choose to divide by 6.68 times 10 carat exchange 27, I predict I will get a foolish answer. All right, I'm going to type it in and see what I get. Of course, I can just recall the previous expression, move the mouse over to the minus key, whoops, and replace it with divide by, enter, and there is a really stupid answer. This is my piece of evidence to you that using the caret key will lead to bad mistakes, because this says a number that is bigger in the numerator than the number is in the denominator, instead of being some answer that is greater than 1, this says, oh no, I have a teeny, teeny, tiny, tiny answer, which is 0 point, then write 52 zeros to finally get to, the 5. Wow, that is so wrong. Why is it wrong? Because your calculator views caret as only talking about the 10 and not about the other number, the 3.97 or the 6.68. So what it really did was 3.97 times 10 raised to the negative 25th power. That's true. Then it divided that by 6.68 because that was the next number it saw. And after it divided this by 6.68, then it multiplied it by 10 to the negative 27th power. And this is, how shall I say it? Oh, I know, it's wrong. Don't do it. Stop doing this. Okay, so after all that, how do you do it correctly? The answer is anytime that you are trying to express a number in scientific notation, please, please, please always type in the number, in this case, 3.97. That actually has a name that's called the mantissa. Second, EE. Now, don't be shy about this. This is the way to do it correctly. This means this is a number in scientific notation, that this is part of that number, not two different numbers, the way the caret interprets it, but one number, the way your science teacher interprets it. And then again, with the exchange key and the 27. Okay, so if I were to divide, let's do it. 3.97, I wrote 2. 3.97 second, EE, exchange key, 27, divide by 6.68 second, EE. In other words, always do all numbers in scientific notation using the second EE key. And by the way, on the Casio, yes, it's the EXE key. That's for exponent, not execute, exponent. And here, exchange key 27, enter. Oh, what I wrote, this is supposed to be 25. None of you corrected me. Okay, points off from everyone. Yikes. Now, 3.97, second EE, exchange key 25, divide by, and here you can see me doing it, divide by 6.68, second EE, exchange key 27, boom, the answer is not 0.000000052 times, it's greater than 1. This says it's 59.4. That's good. That's saying that the mass of a uranium atom is around 54 times the mass of a helium atom. 54, yeah, times, well, 4 times 54, 54 times 4. Okay, so look, horribly wrong answer, correct answer. I'm hoping at this point, well, I've covered 2 of the 3 issues I believe you would need to understand to correctly solve problem 6. Issue number 1, you need to calculate the mass of the thorium atom by subtracting the mass of the alpha particle from the mass of the uranium atom. Issue number 2, you need to understand that using the caret key might sometimes let you get lucky if you're doing subtraction or addition. But if you're doing a multiplication or division, it will lead to a horribly wrong answer. So you must always use the second EE buttons to enter a number in scientific notation. No exceptions. Number 3, to solve problem 6, you need the one principle from this unit on momentum, the sum of all the momenta before, oh no, is equal to the sum of all the momenta afterwards. Our 3-minute bell just went off. I'll see you in 3 minutes. Now, all right, just before break, I put down the third principle that you need to use to solve problem 6. First one is recognizing that the mass of the thorium, how we get it. The second one, understanding the correct way to use a graphing calculator and entering numbers that are written in scientific notation. Now, the third factoid that you have to use to solve problem 6 is to recognize that it is an explosion conservation of momentum problem. What begins as one object explodes into an alpha particle whizzing one direction, and the thorium atom, which I'll try to represent as having a hole now, recoiling in the opposite direction. So that's what recoil means. It means opposite to the main one. When you shoot a bullet out of a rifle, the tiny bullet goes forward at very high speed. The much more massive rifle recoils backwards at a much slower speed due to conservation of momentum. The product of bullet mass times bullet speed will equal the product of rifle mass times rifle recoil speed. And of course, if you're shooting something like a shotgun shell and your rifle's against your shoulder, it can hurt. So, but at least it doesn't go flying off at, 90 miles an hour. All right. So this is how we do this problem. My question for you is, before they explode, and I just use that term because this is a collision going backwards through time, right? That's what an explosion is in collision calculation. This is a one-dimensional, head-on, perfectly inelastic collision. They stick together, going backwards through time. My question is, before this explosion, what was the total momentum? Katie. 2.10 times 10 to the 7th power. And what units would you put with that? Ah, all right. So, classmate, Tanrusi, do you agree? Hence, I have job security as your teacher because this is wrong. This is the departure speed for the alpha particle after it comes shooting out of the uranium nucleus. My question was, what is the total momentum of this uranium atom before they explode? I'm going to try one more student, Matthew. Yes, it would be. Why? Exactly. The total momentum before the explosion is 0 kilogram meters per second because, which I can't write, because you, this is where I get to use bad English. U is at rest. U is at rest. Sounds like bad English, but I mean because uranium is at rest, not YOU, but uranium. That's you. Fun with the English language. Okay, because you is at rest. Oh, yeah, he is. Okay. Huh. All right. What would be the total momentum after the explosion? Daniel, who has left us. He's not even with us anymore. All right. Let me go mark him as left early. All right. Left early. Replacement. And by the way, let me update my records and see who among us is not among us anymore. Just that one student. Okay. Uh, Zara, what would be the total momentum after the explosion? Yes, that is absolutely correct. Thank you. Because that's the whole idea behind conservation of momentum. The sum of all the momentum before, well, at the beginning of the problem, before any collisions or explosions, is equal to the sum of all the momenta of all the particles after the collision or explosion. If it was 0 before initially, then it's 0 after finally. Okay, so next question. What is the momentum of the alpha particle after the explosion? You'll need a calculator. Calculate, please. What is the momentum of the alpha particle after the explosion? You should be looking at the homework handout and therefore know that the mass of the alpha particle was 6.68 times 10 to the negative 27th kilograms. You should also know from the handout that the velocity of the alpha particle was 2.1 times 10 to the 7th power meters per second. And I see I didn't type it in correctly. All right, sometimes 2.1. As a physics teacher, I'll point out to you that the speed of light is 3 times 10 to the 8th power meters per second. So this little teeny tiny alpha particle is coming out like 7% of the speed of light. That is fast. That is really fast. All right, random volunteer. Ray, what do you calculate to be the momentum of the alpha particle? And when you reply, I'm going to call on someone else to see if they agree with you. All right, students, what did you get as your result? Well, your math teacher might put it to you that way. No units? Let's see. Fabian, do you agree? No. So this is your answer. Oh, so that means you agree or disagree? Okay. All right. And students, the one thing I'm going to ask you to do is please don't write it the way your calculator displays it. As I understand it, you have math teachers who are perfectly happy with that. But look, I am from the previous millennium. I'm from pre-technology era, pre-calculators. And in my era, we would write it as times 10 raised to the power, not as e minus 19. This is correct. If you didn't get this, then please review how to enter scientific notation correctly into your calculator. You should have multiplied 6.68 second EE exchange key 27 times 2.10 second EE 7. Enter. Ta-da! Now, who can tell me? Actually, I'm going to call on someone. What is the momentum of the thorium atom after the explosion? Jacob, what is the momentum of the thorium atom after? Yeah, yeah, yeah. Is an incorrect response. All right, someone raise your hand. Who can tell me the momentum? All right, Matthew, what is the momentum of the thorium atom? Please, let's see. Tony, do you agree? And why do you agree with that, Tony? How did he come up with it? Tony, why do you agree with that number? How did he come up with it? Ouch. No. Yikes. Joseph, what did you get? No. Yes. Oh boy. How did you get that? Thank you. That is correct. The whole idea is that we're using conservation of momentum to finally solve problem 6. It says the sum of all the momenta before they explode is equal to the sum of all the momenta after they explode. Before they explode, the initial momentum was 0 because U is at rest, making it sound like bad English. So therefore, the total finally, after they explode, must still add up to 0. We calculated the momentum of the alpha particle is positive 1.40 times 10 to the negative 19th kilogram meter per second. The momentum of the thorium particle must be exactly the negative of this number, so that the two of them add together to equal 0. Here we are. The momentum of the thorium atom is negative 1.40 times 10 to the negative 19th power kilogram meter per second. Finally, using the fact that momentum is equal to the product of mass times velocity, we should use the mass of the thorium atom to solve for the velocity of the thorium atom. To 4 sig figs, instead of the 3 that I gave you in the answer key, what is the velocity of the thorium atom? A little bit of thinking while you do your calculating. The alpha particle is like a bullet. The thorium is like a rifle. It would be wrong to expect the rifle to be moving faster than the bullet. If you get an answer that is faster than 2 times 10 to the 7th meters per second, you've done something wrong. Okay, just to repeat what you just said, students, your calculated velocity was negative 2.10 times 10 to the negative 47th power meters per second. So let's try to review a little bit about exponents. I have something times 10 to the negative 19th power, and I want to divide it by something that is 10 to the negative 25th power based on your mastery of science of dealing with exponents. The answer should be 10 to what power? If this was 1 times 10 to the negative 19th, this was 1 times 10 to the negative 25th. 10 to the negative 19th over 10 to the negative 25th power should be 10 to what number, Josh? Well, I'm going to give you a different question right now. What is 10 to the 8th divided by 10 to the 2nd? How did you get that? Yes, I would say subtract 2 from 8. So what should you do here? Well, it's also negative 25. Oh, man. Didn't say I was going to give you an easy one. Do you still agree that it's negative 44? Oh, okay. So, do you still want to stick with this answer? Good choice. All right, I'm going to call on another student. Sham, what did you get for the velocity of the recoil velocity of the thorium atom? 4 sig figs. Interesting. Well, students, I didn't get exactly that number. You're saying it was 359.39 kilometers per second, which of course means thousands of meters, 359, 390, 359,390 meters per second. Perhaps because I didn't round off at the same point you did, my answer was ever so slightly different out in the fourth decimal place. So therefore, I would say I have to agree with you to close enough 359,000 meters per second. All right, we've just spent the entire period doing one problem.